In this video, I'm going to be describing the AT51 microcontroller architecture. This is one of the older microcontrollers. It came from 1980, but it's still in use today. I've drawn kind of a spectrum here, from simple microcontrollers to more complex computers. So here we have the processors you might see in your laptop or your smartphone, and on the very other end you see the AT51, which is fairly simple. In the middle, I've got the processors that you might find in an Arduino, the AT328, for example, which uses the AVR architecture. So the AT51 is still in use, and this chip here, for example, is the Atmel AT89S52, and they're already up to a 53, and by the time you watch this, who knows what we'll have. The AT51 is a very simple and rather dated microcontroller architecture, but it's ideal for learning microcontrollers because it's simple. It might be used in something like a traffic light or a dishwasher, something pretty simple. So whenever you want to start learning a computer architecture, the first thing to ask about is the memory. The second thing to ask about is the register organization, and then you need to talk about the various instructions that you have and maybe some electrical characteristics. In this video, I'll do all of that, and I'll end with an example showing how we can download a program and run it on this chip. But let's start with the memory organization. Inside the chip, you've got two kinds of memory. You've got the flash memory, which holds the program, and you've got some RAM, which holds the data. So the flash memory is written when you so-called program the chip. You write your program into that, and then during normal execution, the flash memory is not changed. It's read-only. The data memory is very small, and in addition, you can have some external RAM, which is optional, and many applications could get by with the small amount of RAM that's on the chip. So there are two different organizations for computers, and we can talk about the von Neumann architecture and the Harvard architecture. More complex computers that can run operating systems like Mac OS, Linux, or Windows have a single unified memory. You can put the program and the data in the same memory, and sometimes the data that's in memory is treated as just data, and sometimes it's treated as program. So that would be true of these processors here. With the Harvard architecture, you have two separate memories. So the AT51 is a Harvard architecture machine. The program memory and the data memory are separate. So this thing cannot modify its own program while it's executing. Next, let's look at the flash memory. It is 8 kilobytes in the chip that I'm looking at in particular, but different variations of the AT51 architecture might have smaller or larger flash memories. The memory is byte addressable, and it will contain instructions. It may also contain some fixed program data that doesn't change, but primarily it contains the instructions. Each instruction is between 1 and 3 bytes in length. Many instructions are only a single byte, and some are as much as 3 bytes. And so when you want to use the AT51, basically what you're going to do is create your program and then compile it and assemble it on some other computer, producing a sequence of bytes. And those bytes will then be downloaded into the microcontroller's flash memory. And sometimes we say we are programming the chip when we write those bytes into the flash memory. And we do that with something called ISP, or in-system programming. Sometimes we see the abbreviation ICSP for in-circuit serial programming. These basically mean the same thing. There are pins on the chip that allow us to write into the flash memory, and so the idea is that those pins are dedicated to flashing the chip and not otherwise used, which means we can program or rewrite the flash without having to pull the chip out of the circuit board. And we see that in the Arduino, for example. And what we're going to be doing in our demo at the end of this video is using an Arduino separately to do the in-system programming. So I'll show a simple Arduino program that will send the bytes to the 8051 and thereby update the flash memory. And then after you've flashed the chip, you can then push the reset button. It's called RST on the 8051. And in particular, when it transitions from high to low, that will reset the processor. It will set the program counter to 0, and then execution will begin. Next, let's talk about the data memory that is internal to the 8051 chip. It is 256 bytes in size, and that's bytes, not kilobytes. It's really quite small. My laptop, for example, has 16 gigabytes of main memory. And this is an architectural feature of the 8051. So all 8051 chips are going to be limited to this tiny size of memory. But this amount of memory is enough for applications like programming your washing machine or dishwasher. Note that 2 to the 8th is 256, which means that 8 bits are sufficient to address any byte in internal RAM memory. So all memory addresses are only a byte in length. So the 256 bytes are organized into several sections, which we can see here. At the lowest area, we have the memory for the register banks, and then we have something for bit addressable memory, and then here we have general use RAM, and then the upper half of the memory space is used for two different things. In one case, it can be used for additional RAM. So the amount of memory that's addressable on the chip is, well, this is 80 bytes. That's 80 in decimal from here to here, as well as 128 bytes using something called indirect addressing. So this range of addresses here can refer to just general purpose RAM, or it can refer to special function registers in the form of direct addressing. And which of these two address forms is used, that is, which two blocks of memory will be accessed, is determined by which instruction. So some instructions will use the general purpose RAM here, and most of them, however, will use direct addressing and access these special function registers. These special function registers consist of things like registers related to the input-output ports, as well as some other functionality like the program status word and registers and so on. I'll talk about these in greater detail later. I'll also talk about the register banks and the bit addressable memory in detail later. We also have external memory, and any particular application may or may not use external RAM. So it's optional. I say it's not used much, but I really don't have any specific statistics to offer on that to support that. But in any case, there is an address that's provided by the 8051 chip to the external memory system. Sometimes with the 8051 architecture, this is called XRAM. And the address is 16 bits. And then there is a bidirectional bus of 8 bits, as well as some control signals like the write and read signals. So if the external memory is present, then you would use these connections to access it. There are not a lot of instructions that address external memory, so it is rather limited, but you can store data there. Next, let's take a look at the registers. The most important register, the register that you'll be using a lot, is the so-called accumulator register. Almost every operation, every arithmetic or logical operation works on the accumulator, with one operand being the accumulator and the result being placed in the accumulator. All these registers are 8 bits except, as I note, there's a B register, but that's specifically devoted to multiplication and division, so it's only used really in those situations. There's a stack pointer, and the stack lives in the internal RAM, so the stack pointer is only 8 bits in length. This allows us to do things like call subroutines and return from subroutines. There's something called the data pointer, or DPTR. Sometimes it's called just the DP register. And that is a 16-bit register, and it is used to address memory locations in the external RAM. Then we have a set of 8 general purpose registers, R0 through R7. These are each 8 bits. And it turns out we have more than just one set of these registers. In fact, we have 4 sets, or 4 banks of these 8 registers. So there are 8 registers in each bank, but at any one time, only one bank is active. And so we can switch between banks if we need to, and that's particularly useful for interrupt handlers. Right, when an interrupt happens, we need to stop executing the current code, and we need to then execute an interrupt handler service routine, and we need to save the existing registers, and so we can use a different bank for that purpose for the interrupt handler, and then when the interrupt handler is ready to return, it goes back to the original bank, and so the interrupted code doesn't know that it's been interrupted. So these are useful for interrupt processing. We have a program counter that can be up to 16 bits, but as the flash memory on the chip is limited, we don't really need as many as 16 bits to address. In our case, it's only 8 kilobytes, so we don't need, I think it's 13 bits is all we need. There's a program status word, which is 8 bits. And finally, we have the special function registers. These include registers for the I/O ports. And in fact, all of these other registers occupy a space in the special function register area of memory. So next, let's take a look at the instructions of the 8051. Here are 3 instructions for the 8051 architecture. In the first, we're moving a byte from memory into the accumulator register. In the second, we are adding some constant value to the accumulator. And then finally, we're moving that result back into memory. And this shows a typical pattern for what assembly programming of the 8051 would look like. Now I'm showing it in general form here, and then down here I'm showing specific examples. And then over here I'm showing the actual bytes that would be assembled and moved into flash memory. With the 8051 assembly code, hex values are indicated with a trailing H, and immediate data is indicated with a pound sign here. The first byte is always the opcode, and the register that's involved is implicit in the opcode. In all 3 of these examples, the instruction is only 2 bytes in length, and the second byte is either the memory address for the first and the last one, or the actual immediate value in this case. In general, instructions can be either 1, 2, or 3 bytes in length. The opcode is always the first byte, and we can also have immediate data, or possibly a memory address, or we can have an offset for jumps and branches. Those would all be an additional byte. And in some instructions, we have a need for 16-bit immediate data, and we also have a need for a 16-bit memory address for the flash to use for jumps and calls, specifically for long jumps and long calls. So with 8 bits of opcode, we have up to 256 different combinations. 255 of those are defined, and the final opcode is left as undefined, and so that might be used for something specific to a particular implementation of the 8051. But basically, the opcode space is full. We also have a number of special function registers. We can access these hardware registers directly with memory addresses. Remember, they are mapped into the memory address space. So here's an example. It turns out that the A register, it happens to be mapped into location E0 in the RAM address space. So there happens to be an instruction to increment the A register, and that's opcode 04, so it's only a single byte of instruction to do that. But we also have an increment instruction that takes an I RAM address, that is a 1 byte address, to address some byte in the internal memory, and that would include the special function registers. So we can use that instruction with opcode 05 and supply an address of E0, which is the address of the accumulator, in order to increment the accumulator. So both of these would have the same effect. So these special function registers, that is the memory mapped registers, include a number of different registers: the A register, the B register, the program status register, the stack pointer, and the DPTR register, which is 16 bits, is mapped into 2 different bytes in the internal memory. And then we have a byte for each of the 4 I/O ports. So these correspond to the pins on the chip, and there can be up to 4 ports on an implementation of the 8051 architecture, and those ports are mapped into these locations here. And we have a lot of additional registers. They vary depending on which implementation of the 8051 you're working with. For example, the AT89S52 that I have has a bunch more registers, and I'm not going to show these here because they vary. So you should consult the specific data sheet for the chip that you're using to find out about those. There are 2 ways to address the chip's internal RAM memory: direct and indirect addressing. Direct is the most straightforward and easy to understand, and we have instructions such as add to the accumulator, and you supply an address in memory. And here this is for AND. I guess the L stands for logical. So here you are ANDing the A register to some location in memory. And here we are moving a byte from some source byte in memory to some destination byte in memory. And here we are incrementing a byte in memory. These are all examples of direct addressing, and here I'm showing the opcodes. And for direct addressing, memory can be viewed like this. You have an address space of 256 bytes, and we talked about how the first half of it consists of the register banks, something called bit addressable, which I will describe later, and 80 bytes of general purpose RAM. And then the upper half of it is 128 bytes of the special function registers. So all of these instructions will address memory when it looks like this. But we also have something called indirect addressing. And to understand that, let's take a look at this view of memory. Here we see the register banks, the bit addressable, and the 80 bytes of RAM. And if we continue with direct addressing, we are addressing the special function registers. But some instructions use indirect addressing, and for those, addresses in the upper half of the address space, that is, addresses between 80 and FF, will not address special function registers, but will just access the additional RAM memory. So we sort of really have more than 256 bytes, but the address space itself is 256 bytes. So direct addressing is used on most instructions, as we saw with these instructions here, but indirect addressing is done using registers R0 and R1. It turns out you can only use R0 and R1. The other registers, R3 through R7, cannot be used this way. And in the assembly code, we indicate that indirect addressing is being used with the commercial @ sign, the @ sign here. So we can say at R0 or at R1. And those are our only two options here. And in this case, the address itself is in the register, either R0 or R1. And so when you use an instruction such as this, you will be addressing either something in this area or something in this area. And the assembler will see the at sign here and will understand that we are using this instruction and not, for example, this instruction. And so the assembler will assemble a byte for the opcode of 06 and not something else such as 05. So to recap the different kinds of instruction addressing we have indirect addressing, and here's an example with the add instruction, which uses all these different kinds. And here we're adding to the accumulator some value that we're getting from the internal RAM, and the second operand here is either at R0 or at R1. And we could also use direct addressing, and so there's an add instruction where we are specifying a memory location here. And in this case, if it is 80 or above, we would be accessing a byte from the special function registers. And there are also add instructions that can add the contents of some register, such as R5, to the accumulator. And finally, there's an add instruction that adds an immediate value. In this example, I'm using hex 55, and we're adding that to the accumulator register. To give you a feel for the instruction set, let's take a look at some examples, and we can start with the add instruction. It always takes A, and the second operand can be either an immediate value, a memory address, one of the 8 registers, or it can be an indirect addressing situation where the second operand is R0 or R1. And it adds that to the accumulator and puts the result back in the accumulator. There are a number of similar instructions, instructions that have similar formats. There's a subtract, an and, an or, exclusive or, and an exchange. The subtract is a subtract with borrow, if you know about that. The instruction set for the 8051 is not very regular, so if you're wondering whether there's an instruction that can take operands in a certain way, then you basically need to consult the instructions list and try to determine that. For example, we saw previously an example of the AND instruction where the result is placed back in memory using direct addressing. And that's available for the AND instruction, but not the ADD instruction. There's also an add with carry operation with a different set of operands. We have an increment and a decrement instruction, or I should say a set of these instructions, and those can increment the value in the accumulator or using direct addressing somewhere in memory, or increment the value in one of the 8 registers, or we can use indirect addressing to get at and increment or decrement a value in the upper half of the RAM space. For testing and jumping, we have this conditional jump, if not equal, that will compare something to an immediate value. And that something can come from the accumulator, from one of the 8 registers, or we can use R0 or R1 for indirect addressing. And if it's not equal, then we will jump. The target of the jump is given as a relative address. That's a 1 byte offset from the program counter, more specifically from the address of the instruction that follows the conditional jump not equal instruction. So that's a plus 127 or minus 128 up to plus 127 offset from the address of the following instruction. There's also a very useful decrement and jump if not 0 instruction where we can specify the operand as an address in memory, and using that we could specify the accumulator if we want to decrement the accumulator, or we could specify one of the 8 registers And again, it takes a relative address for the jump. To get a feel for the instruction set as a whole, let's start by looking at the increment instruction in particular. We can increment either the accumulator, or we can increment a byte in memory, or one of the 8 registers, or we can use indirect addressing to access the second half of the upper RAM. And so take a look at this table here. This takes 2 pages, and this table shows all of the 256 opcodes. And here in particular, you see the one that's undefined. And we can see I've circled the increment instructions here. So the opcode for the increment of the accumulator is 0, 4. That's the opcode for that instruction. And to increment using a direct memory address, that would be opcode 0, 5. This 2B indication indicates that the instruction requires 2 bytes, and the second byte would of course be the direct memory address. And then for the indirect addressing, we see 2 additional opcodes for R0 and R1. And then for the 8 registers, we see 8 additional opcodes. So there's also another increment instruction. Over here, it's opcode A3, and that is for incrementing this DPTR register. Remember that the DPTR register is 16 bits. This is not a 2-byte instruction, it's only a 1-byte instruction. 2C is a thing that indicates how many cycles it takes. You can ignore that. But it's a single byte instruction. Now, you might think, well, gee, if we've got an instruction to increment the DPTR, there must be an instruction to decrement the DPTR. But in fact, there is not. So that sort of shows you how irregular, I guess, the instruction set is. If you want to know whether there's an instruction for a particular combination of operands, you basically just have to consult this chart. Or there's a second table that's also useful, and here I'm showing that. And this shows all of the instructions, all of the 255 instructions, more organized. So we have some arithmetic operations. I'll just run through this so you can see what we've got here. We've got the add instructions. Here's add with carry, and we have a subtract with borrow. Here we see our increment instructions. Okay, so we see increment of the accumulator, of one of the 8 registers, direct memory address, and here this is indicating that the number of bytes in this instruction is 2, whereas the others have a single byte. And then here we have an increment using one of the 2 indirect registers. And then down here we see an increment of the DPTR register. Again, it's only 1 byte in length. And we see the decrement. Here we see our multiply and divide instructions. Here is a decimal adjust instruction. And then we have the logical operations. We have AND. Here we have OR, exclusive OR. And then we have some instructions to clear the accumulator, to complement the accumulator. And then we have some rotate instructions. Here are a couple of additional rotate instructions. Here we can swap the nibbles within the accumulator. A nibble is a 4-byte quantity, so there are 2 nibbles in every byte. So we swap the 2 halves of the byte. Then we have the data transfer instructions, and we have a number of different move instructions, lots of different combinations. And if you want, you can plow through all of these. We can move data from the flash memory. So here we're moving, C stands for a code byte, and we're using either the DPTR register to access the particular byte in the flash memory. It's 16 bits. We're adding the A register as an index, or we can use the program counter, again adding the accumulator. And we've also got move X, which is moving from the external memory or to the external memory. We've got two push and pop instructions, and then we've got some to exchange bytes. And then here we have some instructions to manipulate individual bits. We have clear the carry, and here we see an example of bit addressing, and I haven't gotten into that yet, but since we're working with individual bits here, we see the bit addressing mode here. And so we see and or and move and some jump testing and the jump. I'll get into that later. Then we get into things like the call instructions, the return instructions. We have several jump instructions, and then we have some jump instructions that test different things, compare and jump if not equal. And finally we have a no-op instruction. So now let me talk about the DPTR register. It is 16 bits in length, so it can address anything within a 64K range. And it's used primarily to access external RAM and for jump tables. So the instructions that can use the DPTR are all listed right here, and the two primary ones are MOVX, both using the DPTR register as an index into external RAM to fetch memory, and so you can fetch a byte and move it into the accumulator, and the instruction that moves a byte from the accumulator into external memory using DPTR as the address of the location in memory to move into. We also need to put something into the DPTR to use it, and so there is a move instruction which takes 2 additional bytes or 16 bits, and it moves an immediate value into the DPTR, so we can move the address of the data that we're interested in. And if we want to walk through some data in the external RAM, we can make use of the increment DPTR instruction to increase the pointer by 1 byte at a time. We can also use it to compute an address for the target of a jump instruction. So we can jump to an address, and that address is given by the value that's in the DPTR register. But first we add whatever's in the accumulator. So if we have, for example, a table of things, a table of jumps, we can use A to compute which one of those we'd like to jump to, and use that as an index. This might be useful for case statements, for implementing switch statements, and that sort of thing. Here is our picture of internal memory with its 256 addressable bytes. So now let's talk about the register banks, which occupy the low 32 bytes of the address space. And I think we can understand the register banks by looking at the motivation for them. So imagine some code is executing and all of a sudden an interrupt occurs. We need to switch what we're doing and execute an interrupt handler function, sometimes called an interrupt service routine. And then at some later time, after the interrupt is dealt with, we will return to the interrupted code. Now the interrupted code had better not see any of its registers modified, yet with the AT51 we can't really do anything without using the registers. So the handler function is going to have to somehow save the registers of the interrupted code and then run, and then when it's ready to return it can restore those registers. And ideally the interrupt handler needs to get to the cause of the interruption quickly, so we want it to run fast. We don't want to take too much time. And the idea here is that the handler will be able to use its own set of registers. And for this purpose, the AT51 provides 4 sets of registers. So each of these 4 banks will contain 8 registers, and at any one time only one bank is in use. That is, an instruction that refers to, say, register 5 will refer to register 5 of the current register bank. So how do we know which bank is currently being used? Well, in the program status word, we have 2 bits that are dedicated to determining that. So these 2 bits select whether we are using bank 0, 1, 2, or 3. And if you want to use a different register bank, well, the code has to modify the program status word. Okay, that doesn't occur automatically when an interrupt occurs. So most likely the first instruction of the interrupt service routine will be to modify these 2 bits here to select a different bank, and then it can store the accumulator and what other registers it might need into these storage locations. And then later, when we're ready to return, it can restore the program status word before it executes the return from interrupt instruction. So to be more specific, here is a map of the low 32-bit bytes of the RAM, the internal memory space. And we see it's simply organized as 4 banks sequentially, and each bank has 8 locations for storing the 8 registers of that bank. So another thing we can notice is that since the register banks are mapped into the address space, we can, in code if we want, address any register in any bank by using direct addressing. Obviously, if we use register addressing, the instruction only will be 1 byte in length generally. And if we need to use direct addressing, the instruction will require an additional byte. But nonetheless, we can address any byte in any bank easily by using direct addressing. Next, let's talk about the bit addressing mode of the 8051. Memory in most computers is byte addressable, and that means that every byte has a unique address, and every memory address refers to a specific byte. It's true that some of the computers in the early days of computing had some funky word sizes and weird stuff going on, but nowadays it's implicit that memory is byte addressable. Well, the 8051 comes from those early days of computing, and it has this other mode called bit addressable, which I'm going to describe now. So remember that in our memory map we had these 16 bytes which are bit addressable. So we can address these 16 bytes like normal, just as we can address the other bytes with direct or indirect memory addressing. But in addition, we can use the bit addressing mode for those bytes. So we've got those 16 bytes of RAM. The locations I just showed you were hex 20 to hex 2F. And in addition, 16 of the special function registers, that is, registers up in this area, are also bit addressable. So we've got a total of 32 bytes that are bit addressable. So notice that 32 times 8 bits per byte is 256. And so with an 8-bit address, we can address any one of those 256 bits, right? It takes 5 bits to address 1 out of 32 bytes, and it takes 3 more bits for a total of 8 bits to address any bit within the byte. So 5 plus 3 is 8. So the addresses of individual bits within these 32 bytes will be 8 bits in length. Most instructions use byte addressing. Okay, so here's an example. The move instruction, one flavor of that instruction takes a direct memory address and it moves, say, some register into that memory location. Here is the opcode for this particular instruction. But some instructions use bit addressing instead. And so there's also a move instruction that uses bit addressing. And here's the general form of that. It moves a bit from, this is the carry bit in the program status word. So it moves 1 bit, and the target or the destination is given not by a direct memory address, but by a bit address. So it has a different opcode, and that opcode is hex 92. And so here, both of these instructions require a second byte to give the actual direct memory address or the bit address. So here I'm specifying 8.1 in both these instructions, and 8.1 happens to be the stack pointer register. So that happens to be the very first, well, I should say the very second register in this region here. But for the bit addressing mode, 8.1 specifies something different. It happens to be port 0, and it happens to specify that particular bit within the port 0 register. Okay, so you can see that bit addresses and direct memory addresses are both 8 bits in length, but some instructions interpret that byte to mean the byte address of some byte in the memory address space, while other instructions interpret it as a bit address to address one particular bit within these 32 bytes that can be bit addressed. So here is a map of all of the bit addressable locations. So as I said, the 16 bytes in memory from hex 20 all the way up to 2F can be addressed with bit addressing. And in particular, we use addresses 0, 0 through 07 for the first byte, addresses 08 through 0F for the second byte, and so on. Okay, this is addressing the least significant bit. This is the most significant bit. For the other 16, we have this particular mapping. Now you should consult the data sheet for the particular chip you're using. This is for the chip I'm using, but it's going to be somewhat similar to this, if not identical. And so we have the 4 I/O ports, 0, 1, 2, and 3. We have some configuration registers for the timers and the serial communication. Here we have the interrupt enable and the interrupt priority registers. And here we have the program status word, and then we have the accumulator register and the B register. So we can use bit addressing, and these others may or may not be assigned for your particular chip. So next, let's look at the instructions that actually use this bit addressing mode. So we've got an instruction to set a bit, to clear a bit, and these are 2-byte instructions, 1 byte for the opcode and 1 byte for the bit address. And here we can complement a bit. Here we can move a bit into the carry. The carry bit is a particular bit within the program status word, and we can test it and jump based on its value if we want to. And here we move from the carry bit into some particular bit. And then we can do and or on a particular bit with the carry bit, placing the result in the carry bit. And then here we can jump if a particular bit happens to be set. And here we can jump if a particular bit is clear, that is equal to 0. By the way, the assembly code uses this sort of notation to indicate bit addressing. So the bit number 3, the fourth bit, 0, 1, 2, 3, 4, of the accumulator would be specified with a .3. And we could also use P1.5 to select a particular bit within port 1. And so that's how bit addressing appears in the assembly code. And then here we have another instruction that we should mention. And what this will do is take a bit address here, and it will jump if the bit was set to 1. And furthermore, it will clear the bit. So this jump if the bit is set and clear it. Another addressing mode is relative addressing, or sometimes we say PC relative addressing. It's an offset from the current program counter. And so the actual offset will be 8 bits, and that will be treated as a signed number, so it'll have a value between minus 128 and plus 127. And it's used for instructions that do jumping. So let's look at the example of the sjump, or short jump instruction. In assembly code, you'd probably use a symbolic label to say where you want to jump to. But what does that get assembled into? Well, the opcode for sjump is hex 80, and then we look at where my label is. So let's say this goes into these particular memory locations in the flash, and that the instruction is right here at address hex 45, and my label is up here at 42. So we want to jump relative to the program counter backwards a few bytes. And the counting occurs from the address of the following instruction. So the program counter would be incremented to hex 47. And the value right here, which happens to be hex FB, is a -5 when interpreted as a signed integer. So we are jumping -5 bytes relative to this location. So 1, 2, 3, 4, 5. This jump instruction would jump to location 42. So note in particular that the offset is relative to the next instruction. If you are using an assembly, if you're writing an assembly code and using an assembler and linker, then you really don't have to worry about that because it would be computed for you. But keep in mind that you'd want to use the short jump for jumps to things that are fairly close. And we'll see long jumps in a second. So here are some of the instructions that use relative addressing. Well, we just saw the short jump, and that jumps always. We also have a jump 0 and not 0, which tests the accumulator and jumps if the accumulator is equal to 0 or, in this case, not equal to 0. And then we have a jump that tests the carry bit in the program status word and jumps if it is not set, that is, if it's clear. Or we have an instruction that jumps if it is set, so it jumps if the carry bit is 1. And then we have some jump instructions that use bit addressing, which we saw before. And one tests to see whether the particular bit that is addressed with bit addressing is clear, and if so, it jumps. And the JB instruction jumps if the bit that's addressed happens to be set to 1. And then we also have this jump and then clear, which tests the bit and then jumps if it's 1, but also has the side effect of clearing the bit to 0. And then we have this clear and jump if not, compare and jump if not equal. So here we are comparing something to an immediate value and jumping to some location, again specified with a relative address. And this operand can be a register A or one of the 8 registers, or we can use indirect addressing with R0 and R1, and it compares it to an immediate value. So this instruction would obviously be 3 bytes, one for the opcode, one for the immediate data, and one for the relative address. And given that there are 8, 9, 10, 11 of these instructions, registers, there would be 11 variations. And here we have a decrement and jump if not 0. And again, we can specify an operand and a relative address. And this is particularly useful for loops where we have a counter and we start the counter with the number of iterations we want. And at the bottom of the loop, we decrement the counter and jump back to the top of the loop if the counter has not reached 0. The counter can be in a memory location or one of the 8 registers. Next, let's look at the stack. We have a register called the stack pointer, and that's an 8-bit, that is a 1-byte value, and it's one of the special function registers, so we can only use it with direct memory addressing. And we have some push and pop instructions as well as the call and return instructions. Now, the stack happens to grow upward in memory. In my diagrams, I show low memory at the bottom of the page here, so the stack is growing upward. And if you are programming in other operating systems, such as Linux, you might be used to the stack growing down from high memory. But here, it's growing upward. And so the push instruction will take a byte and push it onto the memory, increment the stack pointer, and then use that as the address to push or to store into, and pop goes the other direction. Likewise, we have a call and return instruction, and here we are saving the program counter, that is the address of the instruction to return to, and that's a 16-bit quantity. So the call instruction will increment the stack pointer and store a 16-bit value. A 16-bit is 2 bytes. We'll store 2 bytes onto the stack, and return pops those off and puts them into the program counter to return. The short jump instruction has a 256-byte range, so the target must be fairly close to the jump instruction itself, and that won't always work. So there is also a long jump instruction, and the long jump instruction takes 2 additional bytes, and that gives you a 16-bit address, which is adequate to address any byte within the maximum of 64 kilobyte flash memory. There is also a call instruction, and that's in the long form. There is no short call instruction. And again, it takes 2 bytes of address. There's also something called an absolute jump and an absolute call, and these take an 11-bit address. Now with 11 bits, you can address anything within a 2K range. So if the target of the jump or the call instruction is within the first 2K bytes of flash memory, then you can use the absolute jump or absolute call. This is a pretty tight encoding, and you can see that using 3 of the bits in the opcode in order to combine with the 8 bits of this byte here for 11 bits uses up quite a few of the different opcode combinations, and in fact it uses 8 different opcodes for the absolute jump and another 8 opcodes for the absolute call instruction. This might have been appropriate when the ROM size was really under 2K and bytes were at a super premium, which was the case when the 8051 was originally designed. Right now, I think this is a design decision that was made 50 years ago, so it is what it is. There's also a jump that is an indexed jump. That's just a single byte instruction, and it takes the 16 bits in the DPTR, the data pointer register, and it uses those, but first it adds the contents of the accumulator. So if you don't want that, you could always clear the accumulator first, but for implementing, say, a switch instruction, you might want to have some value in the accumulator to jump into a table of jumps. There are a couple of other instructions that I'd like to mention in passing. We have the multiply and divide instructions. These operate on the A and B registers. Then we have a couple of rotate instructions. They rotate either right or left, and they rotate the accumulator, or I should say the bits in the accumulator, by 1 bit position, either directly or also through the carry. Then we have the no-op instruction, and I mentioned the undefined opcode. And we have a return instruction, which I don't show here, as well as the return from interrupt instruction. Both the return and return from interrupt will pop 2 bytes off of the stack and load that into the program counter, thereby returning from the routine or the function. In the case of the return from interrupt, it will also modify the interrupt level. I'll talk about interrupts in a second. Before that, I want to mention the decimal adjust instruction. The decimal adjust instruction works with binary coded decimal. And so let me remind you what binary coded decimal is. This is a technique for storing decimal numbers using bits. So let's imagine that you've got hex 74 and hex 68. If we interpret those as hex numbers and we add them according to binary arithmetic, we'd get hex DC. But we could interpret those as decimal numbers. In other words, we could interpret this hex 74 as a decimal number. normally it's a binary number, so it corresponds to 116 as a decimal number. Hex 68 corresponds to 104, and if you were to add these two things, you'd get 220, which is what hex DC corresponds to. But with binary coded decimal, we interpret hex 74 as the number 74 in decimal. Okay, we interpret hex 68 as the number 68, and then when you add them together, you would get 142. Okay, so when we add using binary addition, we get DC in hex, which is not the answer we want. But interestingly, if you add hex 66 to that in binary, you would get this 142, which is exactly the correct result, interpreting those nibbles as decimal numbers. Each byte can only contain 2 nibbles, so this would be a carry out as well. So that's what the decimal adjust instruction does. In order to add these two numbers, interpreting them using binary coded decimal, what we do is we add them in binary to get hex DC, and then we do the decimal adjust instruction on the accumulator. And what the decimal adjust instruction will do, it just takes one operand, the accumulator, and it will add either 00, 06, 60, or 66 as appropriate to the accumulator. So here we've got a C, that's not a decimal number. We've sort of overflowed. This should have been 2 carrier 1, right? 4 plus 8 is 2 with a 1 carried. And so it adds a 6, and that essentially puts the 2 there and then carries the 1. And likewise, this number here is greater than 9, so again we add a 6 there, and we end up with the correct result, namely 42, which can be interpreted as the decimal number 42 with a carry out. So that's the decimal adjust instruction using which is useful for binary coded decimal arithmetic. And that might be useful if you are programming, say, a microwave or dishwasher, and you just want to display some small number and you want to do it in decimal. Now let's talk about interrupts and how the 8051 architecture deals with interrupts. There are 6 sources of interrupt. At least there are 6 on the version of the 8051 that I'm using. Yours may be different. There are 2 external pins that can cause interrupts, and there are 3 timers that can cause interrupts, and there's the UART interface that can cause an interrupt as well. So as far as these external interrupts go, there are 2 pins, and you can see them here. They are on port 3, bits 2 and 3, and so these ports do double duty, if you will. So maybe these pins are used for general purpose I/O, or maybe they're used for the serial communication or the interrupts and so on, timers, etc. The timers will cause an interrupt when they count down to a particular point, and you can also have an external counting function going on. But in any case, we have 6 sources of interrupts. There are 2 special function registers that are important. One is called the IE, or Interrupt Enable Register, and the other is called the IP register, which is the Interrupt Priority Register. So interrupts can either be enabled or disabled, and that's the function of the IE register. So there is 1 bit per interrupt source to indicate whether that particular source is enabled or not. So 0 for disabled, and the bit will be set to 1 if we are allowing interrupts from that particular source. And there's 1 additional bit, which is called the global enable bit, and if it's 0, then interrupts will not happen. In other words, all 6 sources are disabled. If it is 1, then we can have interrupts depending on whether the particular source is enabled with the individual bit. So we have 6 bits there and 1 bit, and then 1 bit is unused. And that's the 8-bit interrupt enabled register. So your code would initialize that register to indicate which interrupts it wants to receive. Now there are two different priority levels, okay, and that's the interrupt priority stuff going on here. So we have a low priority and a high priority. And let me explain that this way. This shows execution of some code. It's normal execution, and it goes on, instruction after instruction is executed, but at some moment in time an interrupt occurs, and at that point we start executing the interrupt service routine, or sometimes called the interrupt handler function. And so I'm showing the interrupt occurring here, and then at some later point we do a return from interrupt instruction that sends us back to the normal execution of the code that was interrupted. Now, if it's a low priority interrupt, that's what happens. Okay, but then let's imagine that while we're executing the interrupt service routine, we get a second interrupt, and this comes from a high priority interrupt source. So every interrupt source will either be a low priority or a high priority, and it will be assigned a priority when you set this IP register. So if we are executing a low priority interrupt and a high priority interrupt occurs, then we will stop executing the interrupt service routine for the low priority interrupt and switch over to another interrupt service routine, and that will run at the high priority until it is done. And then when it does a return from interrupt, we will return to the low priority interrupt, and then we'll run that until it completes. So again, every interrupt source is either low priority or high priority, and that would be set up initially in your code when you write to the IP, or interrupt priority register. If you want that particular source to be low level, the bit would be 0, and if you want a particular interrupt source to be a high level, the corresponding bit should be set to 1. So there are 6 bits that are defined in this register and 2 undefined bits. And so that's how you initialize the register to determine whether each of these interrupt sources or these interrupt types will run as a high priority or a low priority interrupt. And then low priority interrupts can be interrupted by high priority interrupts, but not other low priority interrupts. High priority interrupts cannot be interrupted, and they would run to completion. And if the high priority interrupt runs to completion and there's another high priority interrupt, then that would happen later after you resume executing the low priority interrupt. It would immediately be interrupted with another high priority interrupt. And so eventually all the high priority interrupts will be serviced, they'll all return, then the low priority interrupt will continue going, and then it would return, and if there's another low priority interrupt waiting or pending, then that would be executed. So to repeat, low priority interrupts can be interrupted by high priority interrupts, but not by low priority sources. Other low priority sources would have to wait. High priority interrupt routines cannot be interrupted. Okay, so what happens when an interrupt actually happens? Well, when an interrupt occurs, the current program counter is pushed onto the current stack, and then we load the program counter with what's called the vector. There is an interrupt vector for each particular interrupt source. Okay, this use of the word vector has nothing really to do with vectors that you might find in math, but instead it just is basically a set of addresses. There's one address for each particular interrupt source. So here we see our 6 sources of interrupt. The reset is also considered another address. So here are the addresses, or the vectors we can say, for these particular interrupt sources and for the reset. And what that means is that when one of these 6 interrupts occurs, or when the reset button is pressed, we load the program counter with that particular address. Okay? And for example, when the reset goes from high to low, that is when the reset button is pressed and released, then the program counter will be loaded with 00. And notice that there are 3 instructions here, at addresses 0, 1, and 2, and that happens to be enough for a long jump. So it's very common for the first instruction at location 000 to be a long jump to something beyond this interrupt vector stuff. And so for each of the other interrupt sources, there is another address. So for example, if there is a interrupt on the external interrupt 1 line, the program counter would be loaded with hex 13, and we would jump to that location where presumably there would be either a very short interrupt service routine or a jump to a longer routine. When the interrupt service routine completes, it would end by executing the return from interrupt instruction. And what that does is change the current interrupt level, meaning that other interrupts at this particular level would now be possible. Okay, so that's how it differs from the return instruction. It would also pop the program counter off of the stack and move it into the program counter register. There are a number of registers or some additional registers for configuring the timers and the external interrupts. And so there's the configuration for the timers, and there's also a configuration register for the serial UART. I'm not going to discuss the UART interface, but the AT51 does contain an interface for serial communication. Here is the program status word. This is an 8-bit register that contains some useful bits that are set and can be easily tested. It includes the carry bit, the auxiliary carry bit, which is used for binary coded decimal. It contains an unused bit that you can use as you want. And then, as we talked about before, it contains 2 bits to select the register bank. And then we have an overflow bit that's used for the multiply and divide instructions. This bit is reserved, and finally you have a bit that indicates the parity of the accumulator. This register is one of the special function registers. It happens to be located at address D0, and it's also one of those locations that can be addressed with the bit addressing mode, which means you can set and test individual bits within the register individually, so that's convenient. So I'm headed toward doing a demo, but before I do that, I want to talk a little bit about the circuitry that's involved. Here is a pin, one of the general purpose I/O pins, that is one of the bits within one of the ports, and this symbolizes the pin itself, and we've got an LED attached to it. Now what's going on inside the chip here? Well, I've simplified a little bit from reality, but I think it'll give you the idea. You can do 2 things to this particular bit of the port. You can read from it or you can write to it. And if you read from it, well, that's pretty straightforward. If you write to it, well, we've got this kind of circuit going on. We've got a pull-up resistor and we've got a MOSFET. This can be thought of as a switch that's either open or closed, and it's driven by the bit in this flip-flop here. So if you write to a port, you write to this flip-flop, either an individual bit or the entire 8 bits of the port. Here I'm just showing 1 bit of the port, but there would be 8 of these for each port. And we've got some kind of control circuitry here that will either load this flip-flop or not, and the actual value to load it with. So if you load it with a 1, there's an inverter here, so this would be off, the switch would be off, and the pull-up resistor would pull this to a positive voltage. Whereas if you write a 0 here, then the switch is turned on and it pulls the pin to ground. Now you might think that this would work here. This is a pretty high resistance value, okay? So the LED will not actually glow very brightly. There's enough here to drive some TTL circuitry, but driving an LED is not really what this is good for. So another way we might do this circuit is as I've shown here. And so here we've got the LED reversed and it's tied to the power here through an external resistor. And when we write a 0 here, that's going to open the switch and that's going to complete the circuit. So when we write a 0 to the flip-flop or to the port, the LED will glow. So it's basically a not function here. When we write a 1, it will turn this switch off, and then there won't be a pathway to ground, and the LED will be off. So write a 1, and the LED goes off. Now this kind of circuitry here is maybe not what you're used to with an Arduino. We can get into a little bit of trouble here. Let's say we do want to do some input from the port, and so you might imagine that what you'll do is a circuit like this. You'll have a resistor that pulls down to ground, and this is a push button to the voltage. And so, but look what would happen if you've written a 0 to this, or if this register contains a 0, then this switch is turned on, and you've got a direct path from power to ground the minute you push that switch, and your chip is fried. And so this actually happened to us, and it turned out that this pin and this port and some of the chip was completely fried. Oddly enough, some of the chip still worked, so it took quite a while to figure out this was what was going on. But you need to be careful here. And so if you want to use a particular pin or a port as input, you need to write FF to it first. And so you'll see that in some of these AT51 programs. They're writing an FF to the output. And what that's doing, it's writing a 1 here, which is turning this off. Okay? And once this is off, then you can just read from it directly. This is a high value resistor, a lot of resistance, so you can still read the value. So basically this thing is not really going into high Z mode or high impedance mode for input like you would have with other chips. For example, when you're programming the Arduino, you set up the pin as either an input or an output, and that basically configures the pin, and then you use it either as an input or an output, and you don't really fry your chip that way. But here we've got this situation, so I just want to warn you about this. So in order to do the demo, we're going to have to program the flash. That is, we're going to have to write the program bytes into the flash memory on the AT51 chip. There are two modes that we can use for this. There's parallel and there's serial mode. The parallel mode is compatible with EEPROM programmers or EEPROM programmers, and it's a little bit more complex. For one thing, it requires a non-standard voltage, requires 12 volts, where the chip otherwise runs on 5 volts. The serial mode is a little bit simpler, and that's what I'll be talking about. No special voltage is required, and it uses the SPI, or serial peripheral interface, which is a 3-wire interface, the MISO, MOSI, and the clock. And we're going to use an Arduino to do the programming. In fact, I'll go over a very simple program that will write the program bytes to the AT51. So we're going to basically create our own EEPROM programmer. And the general idea is that we will start by raising the reset pin, and then we'll send a special programming enable command to the AT51, and that will put it in programming mode. And then after that, we send it a number of commands. There's a command to write a byte to the memory. There's a command to read a byte from the memory so we can verify that it worked. And we have other commands like erase the entire chip. And then when we're done putting the bytes into the memory, we can lower the reset line, and that will perform a reset and start execution at location 000. So now let me show you how we're going to wire up the AT51 chip. This is the AT51 chip, or the particular chip I'm using, which is the microchip AT89S52 chip. And it's got 4 ports, 0, 1, 2, and 3, and some other stuff. But we'll start by connecting the ground here and the power to 5 volts. We also tie this pin 31 high. We'll have an input, and the input will go to port 0, pin 0. And so this push button will pull the pin low, but otherwise this resistor will hold it high. So that will be our input, and our output will be on port 2. We'll use all 8 bits, and each one of those will be connected to an LED through a resistor to the power. And so, as I said before, they'll operate sort of in an inverted way. When we write a 1 to that particular bit, the LED will go off, and when we write a 0, it will go on. The chip has an oscillator, and we could tie a crystal across these with some capacitors, or we could run a straight oscillator into pin 19, and actually that's what I'll do. And then here we have the Arduino over here that we're going to be using to program it. Actually an Arduino Nano Every, and it's connected to a laptop with USB and powered with 5 volts and ground. And here are the 3 lines that connect the SPI interface, the MOSI, MISO, and the clock. The MOSI is master out, slave in, so that's for sending data this way. And MISO is master input, slave output, so the AT51 can send data back. And then we've got the clock signal that will be driven by the master, that is by the Arduino. We've also got the reset pin here, and you can see that when we push the push button high, it will pull this pin high, and then when we release it, it will be disconnected, and this resistor here will pull it low, and execution will begin. And we can also control this from pin A7 on the Arduino. Okay, so when we write a 0, that will essentially close this switch here and pull the reset line to high to 5 volts. So it's kind of a negation here. We write a 0 and we get a 1 on the reset line. And when we're ready to execute, we write a 1, and that will turn this off, and then this thing will be pulled low to ground, and execution will begin. So now I want to do a quick overview of the SPI interface. Here you have the Arduino acting as the master, and the AT51 microcontroller acting as the slave. And the Arduino is controlling things by sending the clock pulse. And the system is fully synchronous. That is, every time there's a clock pulse, exactly 1 bit will be sent from the Arduino to the AT51, and at the same time 1 bit will be sent back from the slave to the master. So the master controls the transmission, and it does that by driving the clock signal. By the way, there's a movement to change the terminology from master and slave to main and sub, but I think the words master and slave are more descriptive and more accurate. I mean, these are words and they describe the roles. Human slavery is a completely different thing, so it's muddled thinking to think that you can have any impact by, just outlawing these words. These words are descriptive. They mean something. What we mean is that the Arduino is acting as a master in the sense that it's telling the slave exactly what to do, and the AT51 is in fact a slave in the sense that it is responding to the clock pulses exactly the way it's supposed to respond. So the way that we will transfer data is that the master will write a bit, that is, it will raise or lower the MOSI pin to send a byte, and then after setting the pin, it will drive the clock high. And then at that point, the slave will be responding, and the master will then read what the slave sends back on the MISO pin, and then it will lower the clock signal. And for each bit, it will do these things, and for each byte, it will do this loop 8 times. The most significant bit will be written first, followed by the remaining bits all the way to the least significant bit. So now let's look at what that looks like for the Arduino code. And so here I'm showing the Arduino code. I've just printed it out, but this is exactly how it is for the Arduino IDE. So I'm defining 4 pins here. for the signals that we're concerned with. As I showed you earlier, we've got 4 pins that we're using on the Arduino, 4, 5, 6, and 7. And so we're giving them names right here. And the setup, we have a setup function where we will do all of the action. I'll go through this in a second. And the loop function won't do anything. So we do all of this stuff once and then basically stop. So the setup will initialize the serial interface, and we'll print a line and set the pin modes. So the master out will be an output, the master in will be an input, the master will drive the clock, so that's an output, and the master will also control the reset pin. I'll get to this other stuff in a second, but we can start by setting the clock low and the reset pin low. And now let's take a look at the function that I've defined here called send SPI. And that's going to be passed 1 byte of data, and it's going to send that from the Arduino to the 8051, and at the same time it's going to receive a byte from the 8051, and it will return that byte to the caller of this function. So this is exactly what I showed before. We are writing something to the output pin here, and then we're running the clock high, and then we're reading something from the input pin, and then we're driving the clock low, and then we're repeating. So to go through this a little bit more carefully, we are doing this loop 8 times, once for each bit, and we've got a data bit byte here, and we'll be shifting it left 1 bit for each time we send something. And so we start by sending, well, let's see, what do we send? We are taking the data byte and we're ANDing it with 1, 0, 0, 0, 0, 0, 0, 0, which basically isolates the most significant bit. And this is an if then else. If that is 0, then we do the else part. We send a low to the MOSI pin. On the other hand, if when we AND that it is not 0, then that means we had a 1 in the most significant bit of the data. So we need to raise the MOSI pin. So here we write either a 0 or a 1, high or low, to the MOSI pin. And then we're going to go through these bits one by one. So we shift the data to the left. So the next time around we'll do the second most significant bit. And we run the clock high. And then we're going to do a digital read from the input pin. And we're going to add that to X. So we're building up this value X, and we will ultimately return it. So we've gotten several bits so far, and each time we get a bit, we shift the whole thing left 1 bit, and then we take the bit that we just got, that we just read from the pin, and we OR it into what we've gotten so far, and we keep shifting. So the first thing we get after this loop repeats will be shifted all the way to the left and will be the most significant bit. And then finally we return that. There are some timing requirements for SPI, and so I have some comments here to delay. The Arduino will be running slow enough that we don't actually need to do any delaying at all. But I just want to have these in here so you know with the SPI there can be some timing requirements, and we may have to wait. We may have to slow the clock down in certain situations for some devices. But in this situation, the 8051 will be able to keep up with the Arduino easily. The first command to look at is the program enable command. This command, like the others, is 4 bytes long, so we will be sending 4 bytes, and simultaneously the Arduino will be receiving 4 bytes. And the bytes we send are these values, hex AC 530000, and we receive 4 bytes. The first 3 bytes we can ignore, we don't really care what they are, but the last byte will be a 69, and we can check to make sure that we actually get hex 69. We have to do this program enable command first. that essentially puts the AT51 microcontroller in programming mode, and so we have to do that first. So to flash the chip, we will drive the reset line high, do this program enable command, then do some other commands, and then run the reset low, and then that will start our execution. So now that we've got this send SPI function, which I showed, we can look at this function, which I've defined, called program enable. And all it's going to do is send those 4 bytes, hex AC, hex 5300, and 00. We're going to ignore what this function returns for the first 3 bytes, and we're going to check and make sure that the value returned for the last byte is hex 69, and then we're going to print program enable OK. If there's anything wrong, we print an error message. So we'll see that when we run the demo. Now there's another command called the read signature command. There are actually several variations of this command, and we can do this command to verify or determine what chip we're dealing with. So there's actually a read manufacturer, a read chip, and then there's a third one which I'm not really sure what it is. But the first command, the read manufacturer chip, we send hex 28000000, and we receive 4 bytes. The first 3 we can ignore, but the last one should be 1E, and I guess that stands for Atmel, the company which was bought, and maybe now it stands for microchip. But in any case, we should read a 1E. And then we can send 2801, so it's a slight difference, 0000, and again we receive 4 bytes, and the last one should be hex 52 for this particular chip that I'm dealing with. Yours may be different. And there's a third one where we send hex 2802, 0000, and we receive the value 06. So we've got a function here called read signature, and that just does that and verifies that we are getting what we expect. So this function will take no arguments and return no result, but it sends 28000000 and makes sure that the first one returns 1E, and we can print out a message if that worked okay. And then it sends the second one, 28010000, and checks the return value to make sure that it's 52, which is the number for the chip that I'm working with. And then we can send the third one, and that code is 28020000. It's return 06, and if everything's okay, we just say that this mystery byte, whatever it stands for, was what we expected. And if there's any problem with any of these, we print out an error message. So next, let's look at the write byte command. Again, that takes 4 bytes, so we send hex 40 first, followed by the address. The address is 16 bits, so we send it as 2 bytes. First, we send the most significant byte, and then we send the least significant byte. And finally, we send the data byte itself. And so this is going to write this byte into this particular address in the flash. Of course, being SPI, we get a bit back for every bit we send. So we get 4 bytes back, but we don't really care what they are. So now let's take a look at the write byte function here. And we see that the write byte function is passed a 16-bit address and an 8-bit data byte. And we send the hex 40 followed by the address. First, we take the address and we shift it right 8 bits, which gives the most significant byte, and we send that. And then we AND it with hex FF, which isolates the least significant byte, and we send that. And then finally we send the data byte itself, and we ignore the return value in all 4 of these. The next command is the read byte command, and that begins with hex 20 followed by the address. And again, it's most significant byte first, followed by least significant byte, and then we send a 00. And in this case, we can ignore the first 3 bytes returned, but the 4th byte will be the actual data. So this will read from the flash and tell us what is stored in the flash, and we can use that to verify that the flash contains what we think it contains. And so let's take a look at that function. We have a read byte function that is passed an address and returns a byte, and it sends hex 20. And then, just as before, in the write byte function, it sends the address, first the most significant byte, then the least significant byte, and then finally it sends a 00, and the value that's returned at that time will then be returned as the result of the read byte function. And now finally we have the erase flash command, and here we send hex AC800000, and we ignore whatever is returned. And this will erase the entire flash memory on the 8051 chip. There's also a timing requirement. We've got to wait 500 milliseconds. With some flash memories, you need to erase an entire page before you can write to anything. Sometimes when you erase it, you set it to all ones, and so the writing actually is writing the zeros into the flash. With the 8051 chip that we're dealing with here, you do not have to erase it first. You can just write it straight away. But there is an erase flash command. And so I made a little function for that, even though I'm not actually going to be using it. And here we see the erase flash command, which sends AC800000, ignoring the return value. And then it just delays for the required 500 milliseconds. So next we can take a look at our main function again and see what's going on with this program here in more detail. So our setup, which is where everything happens, begins by printing a line to the serial port, and if you're an Arduino programmer, this should be familiar stuff. We set the pin mode for our 4 pins that we're going to be using, and then we write to the system clock a low value, and at that point we are ready to perform the reset. So what we want to do is we want to raise the reset line on the chip, and remember we have that negation circuit, so we achieve that by setting the pin that we've labeled pin reset to low, which will send a high to the actual chip. And there's a delay. Not sure if this is actually required, but it's not a long wait, and I don't find myself inconvenienced by a 10 millisecond delay. Then we execute our program enable function, which puts us into programming mode. Then we execute the read signature, which verifies that that command, or I should say those 3 commands, work properly and have the right results. And then we execute the load program function, which I'll talk about next. And finally, after we've loaded the program, we want to lower the reset pin on the chip, and we do that by raising the value on the pin that we've labeled reset. So before I look at the load program function, I want to point out that we have an array here, and I'll talk about the program in detail separately, but here are the bytes that we will be writing to the flash memory. Okay, there are 1, 2, 3, 4, 5, 6, 7, 8, 16, 17, 18 bytes, and they're kept in an array called, appropriately enough, program. So now let's take a look at the program function, and what it's going to do is it's going to start by printing a line. Oh, I do call the erase flash. I guess I misspoke. Maybe this is necessary and I've forgotten. I'll have to test that. But in any case, we erase the flash, And then what we're going to do is we're going to go through this program array. Okay, the size of it is the number of elements in the array. And so we have a little counter here. And for each byte in this program array, we are going to call the write byte function, and we're going to write it to address 0, 1, 2, 3, and so on, all the way up to address decimal 17. We won't be having any interrupts, so we don't worry about overwriting the so-called interrupt vectors, and that'll be okay. And then after we are done writing, we print a line that says we're now verifying it. So again, we're going to do a loop just like before. We're going to go through this array, and for each element of the array, we're going to call read byte, and we're going to pass it the address starting at 0 and then increasing. And we're going to check to make sure the value returned by this read byte function is exactly what is in the array. And if there's any problem, that is, if they're not equal, we are going to print this message and immediately stop. And we'll print which address we failed at. But if everything's okay, then we are going to finally call a function named print memory, which is defined right here. And what we're going to do with print memory is ask it to print the entire flash memory, well, starting at address 0, for this number of bytes, so the size of the program, which happens to be 18. So we're going to print out 18 bytes. Actually, we'll be rounding it to a multiple of 8, but let's see how this thing works. It's past the starting address where we want to start printing or reading the bytes, and for each byte we'll read it and then we'll do some printing. And it's past the number of bytes that we want to print out. So we begin by computing this beyond address, which is the stop address. So we add to start address the number of bytes we want to print, and once we reach the beyond address, we'll just stop our loop. And so we've got a loop here that loops from the starting address. We just use the parameter itself, and we're going to be incrementing it by 16. So every line that we print will have 16 bytes in it. So we're going to increment start address by 16 repeatedly until at some point start address is no longer less than the beyond address. It's either equal to or greater than, in which case we stop. And what do we do for each value of start address? That is, on the first iteration it'll be 0, and then 16, and then 32, and so on. Well, we're going to go through and read 16 bytes. So we're going to call read byte in this loop, and this loop will execute 16 times, and it will read the value from that address, and we're using I as an offset, so we read 16 bytes, and we've got a temporary array here called data, which contains enough space for exactly 16 bytes, and we're going to plug in or store the byte that we get back from the flash into that array. And so once we've built that array, we've just read in 16 bytes. What we're going to do is then print it out right here. And to do that, we've got a character, an array of characters. I've made it extra big, 80, which should be large enough. And we're going to use the sprintf function. This is a C function that is similar to printf, except instead of sending it to standard out, it sends it to someplace in memory. And so we're going to write, according to this format string, a line with a 4 characters, 4 hex characters to show the address. This is the way we specify 4 hex digits with 0 fill. And then colon and some spaces. And then we print out the bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes. And for each one, we print out 2 hex digits. And then we have the actual values to use. First, the starting address, and then we have data 0, data 1, all the way up to data 15. And then finally, after we've built the buffer with this sprintf, we go ahead and send that buffer to the serial output. And so at that point, we should see a printout of what actually went into memory, and so we can visually verify it if we want to, although our verify function should have made sure that everything went in correctly anyway. So now we're going to write a little program, the goal of which is to demonstrate both input and output. And in particular, we want to read the value from a pin, which is controlled by a switch, and we want to write to one or more pins, which will be connected to LEDs. So remember, with my wiring diagram, we are connecting a switch to bit 0 of port 0 here, and we've got all the bits for port 2 connected to LEDs. So here is the program in outline, and it consists of an infinite loop which will read all of the bits of port 0, and then it will look at bit 0 within that byte and test to see whether it's 0 or not. And if it's 0, we're going to write, well, this is hex AA 10101010 to port 2, and if it's not 0, then we'll write the opposite, okay, 0101 0101, or hex 55 to port 2. So here's the code that will do that, a little bit closer to the code for an AT51. So first of all, we are going to be using port 0 as an input, and as I described earlier, we want to write hex FF, or all ones, to any port that we're using as an input. And then we've got two labels here. This is not exactly structured programming. We've got some go-tos here, but bear with me. We're going to start by writing AA to port 2, and then we're going to read the input here and determine what to do. So we're going to read from port 0 and move that into the accumulator, and then we're going to AND the accumulator with the value 1, that is all zeros except the least significant bit being set, and this will tell us whether bit 0 is a 0 or a 1. And if when we AND that we have a result that is all zeros, then we know that that least significant bit was a 0. And so we'll go to loop 1, okay, which will write AA to port 2, and then we'll read again and test again and keep repeating. On the other hand, if A is not 0, that means the least significant bit of the accumulator was not 0, and so we will instead not take this loop and fall through and write hex 55 to port 2. And then instead of jumping to loop 1, we'll jump to loop 2, so we'll test again. So this is our infinite loop that will keep testing and updating port 2. So next, what I want to do is look at that program, and here I've copied it exactly. Port 0 gets FF, port 2 gets AA. We've got a couple of labels here. We're reading port 0 into the accumulator, doing the AND operation, doing the first test and going to loop 1, and then we're writing hex 55 to port 2 and then jumping to loop 2. Now let's see how each one of these is manifested as an AT51 instruction. Keep in mind that port 2 is a special function register at port 0 is at address 80, and port 2 is a special function register at address A0. Okay, so first of all, we want to write to port 0 FF. So we're going to use a move instruction with a direct memory address of 80. Okay, that's the address of port 0. And we're using immediate data here. So the opcode is 75, and then the address, and then the immediate data. And then here's our loop 1. We'll come back to that. but we want to write AA to port 2. So it's the same move instruction, opcode 75, but this time we're writing to location A0 the value AA. And then we are going to input from port 0 into the accumulator, and so that's a move. And we can't move it directly into the accumulator. We have to move it into a register, so why not use register 4? And the address of port 0 is hex 80. So here's that instruction, which is 2 bytes. And then we move register 4 into the accumulator with the 1 byte instruction with opcode EC. Next, we perform the AND operation, and we have an instruction that will AND an immediate value with the accumulator. And so our immediate value is hex 01, and the opcode is 54. Then we test the accumulator. Is the accumulator 0? If so, we go to loop 1. So that's our jump if 0 instruction, opcode 60, and the address here is a relative address. Okay, F6 is a signed binary number for -10 in decimal. So that's -10 from the address of the next instruction. So we want to go to loop 1. Okay, start here, counting back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the address of loop 1. So that's our relative address of -10 from this location here. And then we move hex 55 to port 2, and so that is a move instruction. We've seen that before. Opcode is 75, the address is A0, and the data is 55. And then finally we jump to loop 2, and that's a short jump with a relative address, so opcode 80. And here we have the number signed number for -12, which in signed arithmetic, a signed binary number is hex F4. So if we count back from the next instruction, which we don't actually have, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's loop 2. So these are our instructions, and if we get our code here that we have, let me find that. Here is the Arduino program that we're going to be executing, and we can just verify that these bytes are the same. 7580FF, 75A0AA, AC80, EC5401, 60, F6, 75A055. Do this here. We've got 55, and then 80F4, and then 80F4. So this is our program that we're going to be executing right here. So let's execute it. So here is the program exactly as I described it. We can see the program that we will be downloading into the flash, as well as the setup function, the loop function, the send SPI function, program enable, read signature, the write byte and the read byte functions, the erase flash function, the load program function. And by the way, the erase flash is required. It does not work without that. And finally, the print memory function. So let's go ahead and download this to the chip. So here we are compiling and downloading, and we'll get the serial monitor up here. And we can see that as it executes, it prints out what we expected, that the program enable worked, the signature was verified, we wrote the program, we verified it, and there's the program that was loaded into memory. So here's the circuit as I described it, and let me walk through this. You see the Arduino here, and here's the AT51 chip, and this is a push button for the reset, and then this is the oscillator right here. So starting with the Arduino, we're getting power from the USB cable, and we're feeding that into our power and ground buses here. There's also a capacitor across those, just for good measure. And the white wires are connecting the SPI interface, that's pins 4, 5, and 6, to the 8051. Okay, and that's shown down here, where we see the connections to the SPI on the 8051. We've also got this circuit here from pin 7 with the MOSFET. It's got a couple of resistors and a push button switch, and that's going on right here. Whoops, what am I doing? Loose connection. This is being a little rough with the circuit here. There's the MOSFET right there, a couple of resistors here, and the blue wire comes from pin A7 over to the MOSFET, and the green wire goes to the reset pin on the 8051. Here's the push button switch, and it connects power, and through this white wire here it goes to pin 9, the reset pin. I've also got an LED across the reset pin, so we can test that here, and you can see that the reset pin works. Let's see, what else do we have for the 8051? Well, we've got the oscillator, which is connected to pin 19, as well as the ground on pin 20. So here's the oscillator. It is connected to power right here, and there's a connection to ground right here, and then the output of the oscillator goes to pin 19 on the 8051, and you see that pin 20 is connected to ground. You've also got pin 40 connected to power. That's this one up here, and you've got pin 31 also connected to power, and so that's happening here. And this is our switch. We've got a pull-up resistor here and the push button switch to ground. Well, here's the pull-up resistor, and for the switch I'm just using this wire, and I'm manually operating it. And finally, you've got the LED array. So here we have 8 LEDs with their corresponding resistors connected to power, and that's going on with this little breadboard right here. So we've got our 8 connections plus the power connection, and those are connected to port 2, which are the pins down here. So now we can download the program, and so I'll push the download button on the Arduino IDE, and you can see that it's downloading here, and when it's done downloading, it raises the reset and then lowers it, and now this thing is operational. And so here are the LEDs, and we can operate the input to port 0, pin 0, manually this way, and we can see that it works. So yeah, it works. So there you go. I hope that demo explains and motivates you to learn about the 8051 microcontroller. There are several other features of the 8051 architecture that I wanted to mention, but that I won't be able to go into in any detail. For one thing, there are several timers. These counters will advance automatically, and if they ever overflow, then an interrupt will be generated. They can also be used as counters, and here the idea is that an external pin is used to advance the integer, and so when it overflows, an interrupt will occur, but it's counting external events. You have something else called a watchdog timer, and that's a counter that's incremented on every cycle, and when it overflows, it causes an automatic reset to the computer. And so this can be used to guard against software errors, for example. And so if the software is working correctly and everything's going smoothly, you need to periodically feed the dog, as they say, which will reset the counter. And if the software goes awry or something goes wrong and it fails to feed the dog, then the watchdog timer will overflow and cause an automatic reset. There's also a UART serial interface, so that's rather complicated, but if you are driving an interface to serial, then you can use that. That's with the transmit and the receive pins. There are also two modes called idle mode and power down mode, and these are used to save power. Basically, going into one of these modes will suspend instruction execution, just waiting for the next interrupt. The difference between the two is that with idle mode, the counters will continue to run, but with power down mode, it's the lowest power mode possible, and basically the counters will stop and we'll just wait for an interrupt. I'm sure there's other things about the 8051 chip that I haven't covered and maybe that I don't even know about. For example, I didn't really discuss how the pins work, and in particular how the external memory works. But basically there's an interface so that the chip can send out addresses and data or read data from the external memory that you might also want to know about if you intend to use external memory. In any case, thanks for watching. I hope you've learned something about the 8051 architecture.